Just now, we are going to start another presentation. One of the interim invited speaker, Professor Philippe Mésini, he's going to start his presentation as a live. He's from Institute Charles Sadron, France, and the title is set of Organogelators by freeze fracture FTIR. Professor, do you hear me?
Yeah, can you hear me?
Yes, we can hear you clearly. Welcome. Professor, we have about 3 minutes. 3 minutes later, you can start your presentation.
Okay, thank you.
Okay,
Thank you everybody for listening to my talk. And before I get started, I would like to thank the organizers for giving me the opportunity to give you a flavor of what we're doing here in Strasbourg. So I'm Philippe Mésini. I work in the Institut Charles Sadron, and this is a picture of my lab. And most of the work I'm going to present to you was done by Marc Schmutz, who's the real microscopist in the team, and Jérôme Combet for all the small angle neutron and X-ray scattering. So you're welcome to come in Strasbourg. This is some picture of downtown. It's a very old city. You can see the cathedral that is more than 1,000 years old. So you're welcome to visit us in Strasbourg. What I'm going to talk, sorry?
Thank you for your nice invitation.
Okay.
We are going to, I am going to give information, Professor, then you are start.
I'm sorry?
I am going to give information you when you are going to start in a few minutes, okay?
It's not started yet?
Not yet.
Okay. So okay.
Okay. Because some of our participants want to join us.
Okay. So I will start again.
If there is no problem, thank you.
Okay.
In a few minutes, I will tell you.
Should I go now?
No problem. In a few minutes, we are going to start.
Okay.
Please wait here. Thank you. Yes, Professor. I would like to remind that this virtual congress is recording again. And also, if you are ready, you can start your presentation. Thank you.
Okay, so so I would like first, before I get started, to thank the organizers for giving us the opportunity to give you a flavor of what we're doing here in Strasbourg. So I'm Philippe Mésini. I work in Strasbourg, and this is a picture of my lab. And most of the work I'm going to present today was done in collaboration with Marc Schmutz, who's the microscopist I work closely with, and Jérôme Combet, who's the guy who did all the experiments on small angle scattering. This is some pictures of our city in Strasbourg, like I already told you. So you're welcome to come to us and visit this nice city. This is some picture of downtown. The most famous is our cathedral, which is more than 1,000 years old, and feel free to visit us. What I'm going to talk to you about today is I'm going to do study diamide organogelators, and especially these compounds. They are referred as BHPBN, and the number N refers to the number of our carbon atoms in this ester chain. So we have basically an ester chain, aromatic ring here, and these are the two amide functions. And these molecules are gelator, means that in at few very low concentration in organic solvents, they form gels, like you can see in these pictures. So at room temperature, they're not soluble into the solvent, and you have to heat them up in order to dissolve. And when it cools, gels form, and it's thermoreversible. You can see on the DSC thermogram, when you heat it up, you have a first order transition where the gel melts. So you have a gel here, like a solid-like material, and here's the liquid. And when you cool it back at room temperature, see it goes from a liquid to a solid-like material, also via a first order transition. So this material have many applications as coatings, in cosmetics, in biomedical field, drug delivery. And what I'm going to show you today is how we can study the microstructure, what's inside the gel by freeze fracture electron microscopy. And because I need to check the validity of what I'm doing, we have compared it with small angle scattering experiments. So this is the principle for those of you who don't know what freeze fracture is. The principle of freeze fracture, it consists of freezing the sample. We make a deep freeze of the gel here and at very high rate so that the solvent keeps amorphous. And then the gel is cleaved, and you see that the cleavage is not straight, it's not a plane, it goes along the least resistance area where the self-assembled objects are. Then the gel is kept at low temperature and shadowed by nanoparticle of platinum at an oblique shadowing to make to have this impression here, so that we have area that are shadowed and the other not. And then the carbon is evaporated on the sample, and then the gel is rinsed. So eventually, finally, what you observe, there's no more gel, it's just a replica, and it's collected on the grid for observation. So like I said, why is it interesting to keep the solvent amorphous? Is that what we observe, that the gel doesn't form big crystals. Otherwise, what we would see is just the shapes of the crystals. And so we know, so my colleague Mark Schmutt, because he does that a lot of time, know we have an empirical knowledge of what is a good solvent or a bad solvent for to keep it amorphous. And here are some of the results that we can get. So this is for this compound, BHPV10, and you can see the gel is cleaved, and the mean plane of cleavage contain the main axis of the objects that are mostly cylinders, like you can see on these pictures. So the diameter of these objects is about 30 nanometers wide. And here, what you can see here or here is the remaining amorphous solvent. And most of the fractures occur in a plane that contains the axis of this object, but in 1% of the case, some fracture occur perpendicular to the axis of these objects. You can see here. So this is the amorphous solvent, and these are the same objects, but that stick perpendicularly out of the fracture. And on these pictures, you can see, because of the fast shadowing effect, that the center of the cylinder is hollow. So in fact, they're not plain cylinders, they are just like hollow tubes. Now, what we have done with these objects is to try to understand what are the interactions between the molecules. And it's to probe the interaction between the molecules. We perform some FTIR experiments. And here the blue spectra corresponds to the tubes that you just saw here. So it's gels at room temperature. And you can see here on this area, this is the NH stretching bond of the amide group. And these are bands of the amide 1 and the amide 2 bands. And the shifts are coherent with the fact that all the amide groups are bound together along with H bonds. And you can compare to convince yourself what happens in chloroform. In chloroform, where all the molecules are dissociated, there are no association in the solvents, like the NH are free, and you can see the shift for the amide 1 and the amide 2. And if you compare what happens in the neat solid in the powder, this is the green curve here. So you see that in the powder, of course, all the amides are held together by H bonds. And what is quite strange is that here in the same area, you have the signal for the ester, the CO stretching of the ester. And in the powder, when everything is associated, you have a one single bond, but the nanotube have a special design with a double bond here for the CO stretching. So shows that we have a kind of special interaction between the esters. And this is confirmed by variable temperature experiments. So what we do, we took the solution of tubes and we heat them up till it dissociates, and you can see that all the characteristic band of the tubes can tend to disappear, including the ester. So the conclusion of this is that in the solvent, all the amide groups are held together by H bond between the amides, and we also have this interaction between both esters. And because we have chemists in our group, what we decided to do is that we explore this to have different kind of objects. And we varied here the length of the BHPBN. So we synthesized about 20 compounds. And what we observed is that when the length of this ester is lower than 8 carbons, then we have the self-assembly looks like flat ribbons that you can see here. The still form gel, meaning that we have a high aspect ratio objects, so like long fibers. Between 8 and 12 carbon, we have these pictures. I will blow up this regime in a few minutes. And above 12 carbon, we have twisted and helical ribbons, like you see in these pictures. So this is the regime of what happens between 8 and 12 carbon. And you can see all these nice pictures that we got from freeze fracture TEM. And you can see from 8, 9, and 10 and 12 carbons, we have quite nice nanotubes. 12 is quite an exception because we have a mixture. We have some nanotubes on other, I would say, other kind of objects. And you can see when the number of carbon in the chain increases, when the length of this ester increases, then the diameter of the objects were measured on a statistically decent number of objects, I would say 200 tubes. Then we can see that the average outer diameter increases with number of carbon atoms. And you can see also that we are able to measure the polydispersity. So the variation of the diameter increases with number of carbons. And the question arises, so this is the correlation. So this is the chain length here. And this is how the outer diameter increases. And this is the variation. You can see here the dispersity in the diameters of these objects. And what we were interested in was to know what do we measure. We wanted to estimate all the trueness and the accuracy of what we measure. And the question arises because when we do a freeze fracture, we have a replica, so it's prone to artifacts. Especially we sputtered platinum particle, and they have a given size. And also the objects are more or less deeply embedded in the matrix. So we made a systematical error in measuring this diameter. So that's why we compare it with small angle neutron and X-ray scattering techniques. And I will show you an example of what has been done in ILL on the neutron scattering. So we form the same nanotube, like I told you, just I showed you before, but in a surrounding deuterated solvents, that we have contrast between the deuterated solvent and the protonated objects. And this is the intensity that was scattered by these objects versus the transfer scattering, which is more or less proportional to the scattering angle. And this curves comprises two parts. The first part is a straight line where the variation is close to the q to the -1. And this is very characteristic of very long and rigid objects. So this is the form factor of a rigid rod. And then the second part of the curve comprises many oscillations. And these oscillations describe here the cross section of these objects. And these curves could be described by the theoretical form factor of infinite hollow cylinders, I can see here. And it depends on two parameters. The first parameter is the outer radius, and the second parameter is the thickness. And we can fit this very nicely. So this is a theoretical form factor. And you can see all these series of oscillation here. And in fact, we have to take into account the experimental resolution. And from this curve, we are also able to measure polydispersity, a variation in diameter that we've introduced here with a Gaussian distribution. And so we are able to measure this parameter. So here are the parameters that we can deduce from this fit. So the outer diameter is about 27 nanometers. And you can see why we use this technique, because it's very accurate. It's the accuracy about 1 angstrom. Finally, the only remaining discrepancy between the theoretical and the experimental curve is because we have correlation between tubes, because they are not isotropic. They form bunches or bundle of nanotubes that can be also modeled. So this is how we can measure all the parameters on these nanotubes. So we can do this for all the species I show you, for 8, 9, 10, and 12 carbon. And you can see right from these curves that when the diameter increases from 8 to 9, then the oscillations get narrower, which is correct. And also when the polydispersity increases, then the oscillation are attenuated. This can be seen. So these curves in another representation, these are basically the same curve. So this is the curve here, the same, but it's multiplied by 2 to the 4th. And here it's a linear representation. And in this representation, the oscillation of the cross section are enhanced. And you can see this is for 8 carbons, for 12 carbons. So you see the nice oscillation because these objects are quite monodispersed. And here is an example where the nanotubes are polydispersed. And you can see what I was telling, that the oscillation tend to be attenuated when you compare it with the theoretical form factor. So from this neutron scattering, we're able to also measure the outer diameter and also the real polydispersity. And what was interesting is to compare it with the freeze fracture. So in the blue curves represent what I've shown you. These are the diameter as measured by the freeze fracture. And you can see here the polydispersity. And you can see here what the real measurements done by a small angle neutron scattering. So the first observation that you can do is that the diameter measured by electron microscopy is 2 to 3 nanometers higher than those measured by SANS. And it was a predictable bias because like I said, we sputtered the particle by nanoparticles. And the deviation also higher. The deviation is higher of about 3 nanometers, which is also due to the techniques, which means which includes the sputtering of the nanoparticles. So the freeze fracture reproduces very well what we saw in small angle neutron or X-ray scattering. Just keep in mind that the SANS measurements can be modeled only if you know already the shapes. For instance, for 12 carbon, we don't see any nanotubes, and it's impossible by science to make a model. So we don't have a measurement for this. So it shows that freeze fracture electron microscopy is a very practical and very direct method to see the objects and to measure a size, provided you can kind of predict the bias of these pictures. Now, what we wanted to know is also what is the distribution at larger scale. And this is something because we on TEM, we work on kind of a closed, narrow field. What happens if we have bright fields? And this is why some others have tried to remove the solvent and observe the resulting object by a scanning electron microscope. And if you do so by classical drying, what will happen is just that you will dry the gel, and because of the capillary forces, you will just shrink and collapse the structure of the gels. And this is some examples that were done by my colleagues. These are very nice examples. You can see nice details about the structure of the fibers here or here. But what you don't see is that all the fibers are crushed on themselves. They are kind of collapsed. So it does not, it reflects correctly the structure of the fibril, of individual fibril, which is a very rich experiment, but we don't know anything about the spatial, the natural spatial distribution at larger scale. All right. And that's why we kind of developed what happens if we dry in a different way by supercritical drying. It consists to exchanging the solvent by liquid CO2 at high pressure, like in this diagram. So instead, this is the classical drying when we start from a liquid phase and just evaporate it. And the supercritical drying consists in exchanging the solvent. So we are somewhere at high pressure around here. We heat the CO2 at above the critical point, and then we release the pressure. We let escape the CO2. So what we get is something that has no more solvent, but which has not gone through this threshold between liquid and gas. So it's a supercritical drying. When you do so, you can what the object that is obtained, the objects that are obtained are aerogels, which is basically a gel where the solvent is replaced by air and it keeps its alveolar and structure, which is quite different of the gel. So it keeps the natural distribution. You can see this example. It's silica aerogel made of a gel of silica particles. So this is what we did. So we start from our gelator. We self-assemble in solvent, and this is a freeze fracture micrograph of what I showed you already. So you can see the tubes. And then by supercritical drying, this is what we get. So this image are not the same because you see here the scale is much higher. And here, what you can see here, this object that you can see are not single tubes, they are bundle of tubes. Okay, and even now we can observe this aerogel at larger scale, and you can see here what we obtain. So when you look so, and now you can see at larger scale that we have two kinds of areas. We have these spherical objects that contain a high density of fibers, like here, here, or here. And we have looser area that contains less dense, I would say they are less densely packed with fibers. So two area, denser one and looser one. And what is the origin of these heterogeneities? Does it reflect the real structure, this native structure, or is it an artifact during drying process? Maybe like pocket of solvents that were not well exchanged with the CO2 liquid. And to explain that, we decided to come back to some thermodynamic studies. And what we do is that we mapped out the phase diagram like here by two methods, by differential scanning calorimetry, you can see. So we heat the gels like here, and we see when the gel melts. And for instance, here by rheology, we just observed when we measure both the elastic and loss modulus and we heat, and when G prime becomes lower than G double prime, the crossover points shows that we have a transition of a solid-like material to a liquid. And we can do this for different concentration here, and for each concentration, you can map out the gel to sol transition. And what we did in this phase diagram, we did for a huge range of concentration, more than 2 decades of concentration. And we can observe two regimes in this phase diagram. First regime when the melting temperature increases with the concentrations, and then we reach a plateau here. And why do we get an invariant here? And we just made a simple optical microscopy here. And in this area, what happens when the gel melts, it doesn't melt to form a liquid, it forms a biphasic liquid. So we have a liquid-liquid phase separation here. So it means that in this phase diagram is more complex, and we have a liquid-liquid domain here. So you can see clearly here, when the gel forms, it forms this kind of spherical object that becomes a solid. So we have droplets of solids that are included in the fiber, which explain the morphology of the gels. So by these studies, we were able to show that for large concentration, it is very normal that we've got two kind of objects, and that it's not an artifact. So the critical, the supercritical drying affords real picture and the real distribution of our gelators. And it's really important for many application catalysts. I will show you at the end some of these applications. At very low concentration, these objects, these molecules still self-assemble, but don't form any more tubes, but just helical tapes, like you can see here. And it's 100 times more diluted than the previous image I showed you. So it's in a liquid phase, and when you have just deposited on the carbon-coated grids to observe this, and it has been shown in the literature already that helical tapes, like in here, are precursors to full nanotubes. And we took advantage of this image to we use these objects as porogen to make mesoporous materials. So in the literature, you have many mesoporous material. Most of them are inorganic. Most of them are silica or alumina mesoporous material. They are powders. So there's a need for polymeric mesoporous material because of the mechanical properties. They can be more processable. And also, I will show you in a few minutes that they can be also chemically functionalized more easily than mineral stuff. In the literature, we'll find a few examples of these people who have tackled this problem. There are basically two different strategies. One is by using block copolymers, because block copolymers tend to self-assemble in a structure that can form cylinders, and one of the part can be degraded more easily than the other. Another strategy is to use a supramolecular template. It was developed especially by Ikala, where one of the block can be dissociated and leave these spores. And this is pretty much the strategy that we have followed. And in fact, this strategy was proposed a long time ago already by two different groups, the one of Martin Möllers and the other by Dick Weiss, and developed by some other. But the solution is very simple, is that we start from an isotropic solution, and when it cools, it forms these gels, which is still thermoreversible if you have a regular solvent. But instead of a solvent, we took a mixture of monomers, cross-linkable monomers, and at this stage, we make a photopolymerization. So we obtain a resin that contains all the objects, and then we leach this object. We dip it in the solvent, in a dissociating solvent, to take out the self-assembled molecules, and it leaves this white object that are in fact empty pores. When this author tried to develop this object, they had organogelator with huge size and diameter distribution. That's why we took advantage of having nanotubes with low dispersed diameters to see what kind of imprints we can have. And this is the technical, how we did technically. These are the monomer and cross-linkable monomers used. This is the photo initiator to make the photopolymerization here, and the leaching solvent was a chlorinated solvent. So we can make small plates, small cylinders. Of course, the size, what is limiting the size or the thickness is that because we're doing photopolymerization, we have a depth of penetration of the UV. And these resins, we cut them in small, in micro slices with an ultra microtome. And we got slices about very thin slices that can be observed directly under the microscope beam. And you can see that before leaching, this is the resin, and you can see that we have these objects that are included. You can see because we have contrast, they have different contrast. And when we leach them, of course, the contrast increases because we have white pores. It's white because there's no more material surrounded by the resin here. And when doing so, you can see here that we have the helical tapes I was talking about a few minutes ago. So these are the helical tapes, and we did a tomographic reconstruction here. And on this little movie, you can see it's just defocusing. And if you follow the shape of the objects here, you can see the trace of a helical objects. And these white objects here are just objects that run across perpendicular to the section. And you can see when it's defocusing, you can see it forms like a vertex, showing that all these objects are more or less helical tapes. So we succeeded to making a good replica, meaning that with high resolution, we start from helical template and we obtain helical mesopore, which means that the resolution of these molding is about a few nanometers. So we are quite happy with this. Now, if we increase the concentration here, then this is the object that we got. We have the mesopores here. And we can, from the TEM experiment, we can measure the diameters of the whiter area here. And this is the mean diameters of the pores that we get and polydispersity. And so the template is 27 nanometers, and what we got is about 40 nanometers. And we also did nitrogen adsorption porosimetry to measure the diameter of the pores, and this is what we obtained. So we got a good agreement. And like I told you, it's also possible to make some chemistry inside the pores. So we start from monomer that is functionalized, and we still have, we can manage to insert some functions inside the pores. And we took advantage of this to tethered enzymes to make supported catalyst. This is one example of this application that was done thanks to our microscopic studies. So it's the end of my talk. I would like to acknowledge some of the people who worked with me to make the phase diagrams, the synthesis of the molecules. Like I told you, I work with many people, including my local contacts on a large facility. I would like to thank again Marc Schmutz and Christian Blanc for microscopy facility, and these people for DC. And this is the money providers. And finally, I want to thank you for your attention. I will be glad to answer your question.
Thank you, Professor, for your nice and very interesting presentation. Just now, I want to ask all of our participants, do you have any questions? If you have any question, you can write your questions to chat part, or if you want to ask your questions to Professor Mésini, please write the chat part about you have a question. We can open your voice on the system. Thank you. I think there's no question for now. And end of the virtual conference congress. If anyone want to ask any question for this presentation to Professor Mésini, you can send an email to him. Thank you, Professor, again.
Thank you. Thank you so much.
You're welcome. Just now, we are going to have a coffee break about 10 minutes. 10 minutes later, we are going to be here for last section of this conference.